Hi, everyone. Today we're talking about two-dimensional collisions. So instead of just head-on collisions, as you can see right here, we're going to start using two dimensions. We're going to go into the X and in the Y dimension when we analyze two objects colliding together. So first question asks, list the variables that could be measured in this collision. So when we look at these two masses, one is traveling along the x-axis, one is sitting stationary. Then after they collide, it's kind of skewed. You can see that it's not on the x-axis, so it has this glancing blow, right? It hits it at an angle. So it goes off in two different directions. So the things that we can measure, right? We've got M1 and M2. Okay, you can measure mass. And I'll just call it mass, right? You can measure mass. Okay, you can measure the angles. Notice that this is theta, and we have this Greek letter phi down here. Phi is just another Greek letter that we use to talk about an angle. Then another thing you can analyze is the initial velocities. So there's VI in the X and VI in the Y. And then there is the final velocity, VF in the X and VF in the Y. Now this is going to be very similar to kinematics, where things that happen in the X are completely independent to things that happen in the Y. So these are the things that we can measure, right? These are the fundamental variables that make up this collision. Now, what we want to do is we want to write equations. We want to shoot for 4 that could give you an algebraic power that you need to overcome unknowns in 2D collisions. Okay? Now, these are true under very specific circumstances. Okay, this is, for example, if they have equal mass. If one is stationary, and if it's elastic. If these are not met, then some of these may or may not be true. Okay? So we know right off the bat, all collisions have conservation of momentum, right? You've got summation of momentum initially equals summation of momentum finally. But now with 2D collisions, you can actually split that up and say that momentum is conserved in the X. And then you can say that momentum is conserved in the Y as well. Okay? This is true for all collisions. Now, for the next ones to be true, you need to have this special circumstance where you've got equal mass. One is stationary. It's an elastic collision. First, the conservation of kinetic energy, right? We talked about that when talking about elastic collisions. Conservation of kinetic energy is reserved just for elastic collisions. And the last one I want to bring up is that theta plus phi can also equal 90 degrees if they have equal masses. One is stationary and it's an elastic collision. This is, for example, like when you're playing pool, right? Assuming the balls have relatively similar mass, all of them should be stationary except for the one you're using, the cue ball, and then they are understood to be, for the most part, elastic collisions. So these two are kind of conditional, but these two are for everyone. All right, now we will apply that to a practice problem. So we have a 0.3 kilogram puck initially at rest on a horizontal frictionless surface, and it is struck by a 0.2 kilogram puck moving initially along the x-axis at 2 meters per second. After the collision, the 0.2 kilogram puck has a speed of 1 meter per second at an angle of 53 degrees above the positive x-axis. So let's draw this first before we do anything. Right? So let's see. We have I'm going to call them M3 and M2, just to make, if we use 1 and 2 with one of the masses being 2, it can be confusing. So we've got the M3 sitting stationary, right? But then M2 is coming at it along the x-axis, but it's not going to collide head on, right? It's going to collide at a glancing blow. So M2 is initially traveling at 2 meters per second. It then travels at 1 meter per second, and that is at an angle of 53 degrees. Okay? Then when M3 gets shot off, it will then travel at an angle theta at some unknown velocity. Okay, so that is the situation we're dealing with. Now, if this is inelastic, it's not an elastic collision, will the 90-degree or conservation of kinetic energy rules work? Oops. Will those work? The answer is a big fat no. No, they won't work. We'll actually show this as we work. Once we find the angles, we'll add them up and show they do not equal 90 degrees. And then at the end, C actually asks, what is the percentage of kinetic energy loss? So we can actually find how much kinetic energy was not conserved. So we will do that as we work through this problem. So anyway, so part B is the actual question. Calculate the velocity of the 0.3 kilogram puck after the collision. So I'm going to get our givens first. We've got M2 is 0.2 kilograms. M3 is 0.3 kilograms. The V2 initial is 2 meters per second. V3 initial is 0. It sits at rest. Then we have V2 final. Okay, that is 1 meter per second. And V3 final is what we were looking for. Then we know that phi, the angle for the M2 puck is 53 degrees. And theta, again, we don't know. We need to find it. Is that everything that we needed? I believe so. All right, so let's get to work. The equations that we have here, okay, we can't use all four. Remember, the 90-degree trick and the conservation of kinetic energy trick doesn't work. But what we do have is the summation of momentum. So we'll do summation. We'll do summation in the y first, just because I know it's going to be a little bit more simple because there is no momentum in the y to begin with, right? So all velocities initially are either in the x-axis or a 0. So we will start with 0. And then you get M2 V2 y final plus M3 V3 y final. Okay. But we want V3 y final because we can already figure out V2 y final. Okay. V2 y final will equal V2 final times sine of phi. Okay. And we can show that right over here, right? So if we have some angle phi, and we know that this is 1 meter per second, and we want V2 y final, you would do sine theta to get, sine phi to get the opposite, right, instead of the adjacent. So if we want to solve for V3, you subtract the other side. You've got negative M2 V2 y final divided by M3 to get V3 y final. So you've got negative 1 sine of 53 degrees divided by, oh, whoops, that's not a 1. Oh, no, I didn't include M2. That's what it was. Okay. M2 is 0.2 times velocity 1 sine 53 degrees, all divided by 0.3. I knew that looked wrong. So you got V3 y final. That will give you 0.532. meters per second. Good deal. So that's in the y direction, right? Then if we want the x direction, that's actually going to take a little bit more work because there is initial momentum in the x direction. Okay? So M2 is moving in the x direction initially. M3 is not, it's 0, so it doesn't have momentum. So then we have M2 V2x final plus M3 V3x final. And again, we want V3x final. We're looking for the V final. So let's subtract and divide. You've got M2 V2x initial minus M2 V2x final, all divided by M3. Right, we got some room. So we've got, I'll factor out that mass, the M2. Then you've got the Vx initially is a full 2. Then you minus the V2xf, which would be 1 cosine phi, which is 53 degrees. And that is all divided by 0.3. Just to show that, right? If we want this right here in the x would be V2x final, right? So to get the adjacent, you would use cosine. And this equals V3xf, which is 0.932 meters per second. All right, yeah, 932. Yep, good deal. Sorry for the penmanship, I was running out of room. So we have the x and y component of V3f. You can do the trig and find the theta and then find your v, but you can just use Pythagorean theorem if you'd like. You need V3 final. That would be the square root of the x component squared plus the y component squared. And that will come to 1.07 meters per second. Then if you need that angle theta, let's see, we've got our triangle. Okay, in the y was 532, and x was 932. So if you need the angle theta, you would do the tangent inverse of the opposite over the adjacent. So you've got 0.532 divided by 0.932. Now, also keep in mind that if you want this to be as accurate as possible, we would actually make this trajectory more realistic. Because remember, this is going below the x-axis. It is actually going down, right? So this would be 0.932, and this would be negative 0.532. So if we throw in a negative up here, okay, then that will give you, is it negative 29.7 degrees. So your full answer, right, since we're in 2 dimensions, your velocity is a vector. It has to have the direction with it. So your V3 final, the velocity of the 0.3 kilogram puck after the collision, is 1.07 meters per second at, you can say negative 29.7 degrees, or you could say 29.7 degrees below the x-axis. Either is suitable. All right, good deal. Now, that was not the last piece, right? It does also ask us to find the percentage of kinetic energy lost for part C. So to find kinetic energy loss, you need to take what is the change in kinetic energy and then divide that by the initial energy that you had to begin with, right? So this would be Kf minus K initial divided by K initial. So let's find Kf is going to be the harder part because there's kinetic energy for both parties. You've got 1/2 M2 V2 final squared plus 1/2 M3 V3 final squared. So you've got 1/2, let's see, there's 0.2 times 1 squared plus 0.3 times 1.07 squared. And that will come out to, whoops, goodness. That comes out to 0.27 joules. Okay, that is your kinetic energy final. Then if you need the K initial, remember M3 was not moving, so you just have the 1/2 M2 V2 initial squared, which is 1/2 times 0.2 times its initial velocity of 2 squared, and that will come out to 0.4 joules for K initial. All right, let's move you out of the way. I was going to use that area for my maths. So you're down there now. So if we use K final, 0.27 minus 0.4 K initial divided by 0.4, this delta K divided by K initial comes out to negative 32.5% drop. So not only is there obviously some kinetic energy loss, but that is a large amount of kinetic energy that was lost during that collision. Right? This is a big percentage of kinetic energy that was lost. All right, so that is all we have for this one. It's a real quick 2 slides over 2D collisions. Next video, we're going to continue on. We're kind of done with collisions, and now we're going to be moving towards center of mass for the next video.